Hello everyone, welcome to the Energy Harvesting Laboratory channel. I am Kang, and today I'm gonna talk about an eye-catching technology, a self-powered electrical bandage based on body-coupled energy harvesting. Chronic wounds are a severe pathology. When you consider their fatality, you may be very surprised. According to statistics, untreated chronic wounds lead to amputation in 30% of patients and further contributes to a 50% 5-year mortality rate. Furthermore, more than 30 million people worldwide suffer from chronic wounds, and the volume keeps growing due to aging and lifestyle diseases such as diabetes. Due to severity, the chronic wound care market size has become substantial, reaching 14 million US dollars and growing rapidly at a CAGR of 5.4%. Electrical stimulation is a promising and market-approved treatment for wound care. It promotes wound healing by encouraging cellular migration, proliferation, and cell signaling. However, conventional transcutaneous electrical stimulation requires a bulky device with an external power source and demands clinical personnel. Indeed, it also cannot be conducted continuously, which costs a lot of time and resources. To achieve continuous, effective, and convenient electrical stimulation, power transfer mediated by radiofrequency near-field induction or energy harvesting has been investigated. Although RFID and NFC-based devices are thin and flexible and enable high power transfer, but they still require an external transmitter, and the human body blocks power transfer, limiting their practical applications. When it comes to energy harvesters, biomechanical energy harvesters, autonomous electrical stimulation is available by leveraging the biomechanical energy of the human body. However, the stimulation is instantaneous and intermittent, and it requires a lead between an energy harvester and a stimulating electrode, which is very impractical at the moment. In this work, a self-powered electrical bandage termed SEB based on body-coupled energy harvesting is investigated. The SEB harvests 60 Hz electromagnetic waves from surrounding electronics or power lines mediated by the human body and directly stimulates the wound. It consists of a pair of electrodes, one dry and one insulated, on a flexible polyimide substrate. Continuous electrical stimulation promotes cellular migration and proliferation of fibroblasts and modulates leukocyte immune regulation, resulting in fast wound repair. Next, the working mechanism and output characteristics of body-coupled energy harvesting are demonstrated in Figure 2. The human body is a capacitive conductor and is polarized by 60 Hz electromagnetic waves from surrounding electronic power sources. This electrical potential is transformed into an electrical potential across the wound between a dry electrode and an insulated electrode by capacitive induction. The stimulation voltage for steam can be calculated by subtracting the voltage at the insulated electrode Vd from the voltage at the dry electrode Vr, reaching tens of volts. This is confirmed by Fourier transform analysis, finite element simulation. We found that free steam decreases at longer distances from the EM wave source, and it is very constant across every electrode area. Most importantly, free steam is almost constant at every body location applied, indicating its significant advantage in wound healing applications, enabling consistent electrical stimulation regardless of the position. To improve V-STIM, a high permittivity PVDF TRFE CCTO nanocomposite was utilized. PVDF TRFE and CCTO are high permittivity polymers and nanoparticles, respectively. 28% CCTO content increased with STEAM by 19.6%, and interestingly, an elevated CCTO content above 28% decreased with STEAM due to leakage current reducing polarization of the nanocomposite. The wound healing effect of electrical stimulation by the SEB is investigated through a series of in vitro and in vivo tests. In cellular tests, electrical stimulation with a voltage equivalent to V-STIM of the SEB improved cellular migration and proliferation, and the upward expression of relevant genes was observed. Also, this effect was also demonstrated in a mouse model experiment, and the SEB was highly effective in accelerating on wound closure, even more than commercial ointment and Bandage treatment. In one tissue, while the control group showed hyperkeratinization, or representative negative consequences of untreated wounds, we observed active development of granulation tissue and blood vessel formation, indicating the superior effect of the SAB on wound healing. Through a PCR analysis, the SAB enhanced the expression of CXCR2, which is related to immune regulation and other relevant genes that act on proliferation. Thank you for watching this video, and please keep interested in our research. Thank you.